Hello, my name is Georg Götz and I'm an audio research engineer here at Treble. And in the following two notebooks, I want to tell you how you can use the Treble SDK for your machine learning efforts. As Finner already showed you in the previous notebook, we have conducted measurements in this room, and we have matching simulations where we were very careful to match the measurements as close as possible. In this notebook, I want to show you how we can use the simulations and compare those with the measurements while evaluating on a neural network for speech distance estimation. The outcome there is that we can show that when the measurements and the simulations match very closely, the same applies to the machine learning evaluation. So instead of running lots of measurements, you can also run the simulations with the Treble SDK and get equally good insights about your machine learning model performance. And I want to start by just reading in the simulations that we have done. And I can show you once again how this looks like. In here we have a couple of source receiver configurations, but because these were done similar as the measurements, we only have a couple of them. In fact, it's only 20 source receiver configurations because doing the measurements just takes a lot of time and it's kind of costly. That's why we only have so few points at first. And what we want to do is we want to do speech distance estimation, as I already said before. And you can think about this similar as in this application scenario here in the picture. We have somebody who is speaking with a friend, and the friend, for example, has some AR glasses or some other wearable that has a microphone on it. And the person is speaking, and we record the speech with the microphone. And from that recorded speech, which might be, first of all, quite noisy because we have background noise in there as well, but most importantly, it is reverberant because we are usually inside of rooms. And based on that reverberant noisy speech, we want to estimate the distance between the speaker and the listener. And this information is very important, for example, if we want to run some speech enhancement or de-reverberation algorithms on the AR glasses or on the wearable device. And I want to use the following neural network to showcase how we can use the Treble SDK and the simulations for evaluating a neural network. This network was proposed in this paper that you can see referenced here. And what we're doing to evaluate this network is that we have dry speech signals, which we take from a speech database, and we have either simulated or measured room impulse responses. And if we convolve both of those together, we get reverberant speech signals, and then we can also add background noise to them to get our noisy reverberant speech that we would capture with the microphone on the device. We then import this noisy reverberant speech to the neural network, and the network tells us the estimate of the source receiver distance. Of course, we also know a ground truth in this evaluation scenario because we have set this up as measurements or as simulations, and then we can compare this ground truth distance with the estimated distance from the network. If we do this over the entire evaluation data set, we can calculate a mean absolute error. And in this case, for the figure, we of course only have one item that we compare. Therefore, the mean absolute error is just the difference between the ground truth and the estimated distance here. And what we're doing now is that we are reading a pre-trained checkpoint from this model. So it's really important to emphasize that no simulation data or no measurement data from our side was used in training this model. We are just using the data now to evaluate how does the model perform. And to do that, we first have to calculate the ground truth for the source receiver distance. And we do this quickly here for the measurements, which is just one for loop where we calculate the distance. And as soon as we have done this, we can set up our PyTorch dataset for the evaluation. And as I said before, in this demo, we have two evaluation datasets. The first dataset is using the measurements from the lab environment, and the second dataset uses the Treble simulations that are replicating the measurement setup as closely as possible. So we are reading in both of those datasets, and now we can already start to evaluate the performance. So first we evaluate the performance on the measurements. And if we do this, we only have a couple of items here, so the evaluation is quite quick. And we see that our mean absolute error is 1.57 meters. And now, after this is completed, we can also run the evaluation on the matching simulation. And we see in this case, our mean absolute error is 1.54 meters. And already by just looking at one number, we see this is a very close match, but one number can of course also be a bit deceiving. That's why we have a closer look at all of the evaluation responses. And we see here on the left-hand side all of the evaluation outputs for all of the 20 measured and simulated source receiver configurations. And on the left side, we have a box plot summarizing all of those for the Treble simulations. And on the right-hand side, we see all of the responses from the measurement. And we see both of those box plots match very well. So we can say that the evaluation performs equally well on the Treble data as on the measurements. And we see a similar trend if we look at all of the items that we get out of the network and have a look for each of those, what is the evaluation error on the Treble data and what is the evaluation error on the measured data. And we see a very clear tendency that they coincide. But now what we can very easily do with the simulations is that we evaluate on more receivers. So what you see on the left picture here is what we have done so far. We have only a handful of source receiver configurations that we measured and simulated. And now we might want to have a closer look at our network and see if the network also performs equally well at other source receiver configurations. Doing this on measurements can be a bit difficult, time-consuming and slow, because whenever we move the microphone or the sound source, we have to do this manually, and this is a lot of work. Doing this in simulations, on the other hand, is very easy and straightforward. We just add a couple of more lines of code and add more source receiver configurations to the simulations. And there is also the added benefit that the simulations are very, very reproducible, as opposed to the measurements, where you also have to be very sure to measure your source receiver configuration and especially the positions of your sources and receivers very accurately. So let's have a look at another simulation that we ran from the same environment where we added more receivers. And as you can see here, we have now added very many receivers in there, and they are on a very dense and fine grid of receivers throughout the room. So by using this simulation, we can get a bit more, or actually a lot more comprehensive overview of how our model performs on this specific task in this specific room. So let's set up the dataset again and run the evaluation once again. And because we have now so many source receiver configurations, this takes a bit more time. But this is also then down the line very interesting for us because we have more receiver configurations. We have just a better overview of how does the network perform. So let's wait until this completes. All right, the evaluation completed, and we see now a mean absolute error of 1.62 meters, which is still very similar to what we saw before, but we can also now, of course, have another closer look at the results. And we see here on the left side the treble simulations with only few data points. In the middle, we see the measurements with the matching data points. And on the right side, we see the treble simulations where we have a lot more receiver positions in there. And we see, of course, there are similarities between all of those, but what is very clear as well is that we have more receivers, and some of them seem to be outliers where the performance of the network is not as good as for the 20 selected points that we were able to measure. So this is of course very interesting for us, because without having to do lots and lots of measurements, we get a lot more information about the performance of our model. And now we can also easily have a closer look. What are problematic positions, for example? And now I'm plotting the source receiver configurations with the 20 highest errors. So these are the 20 cases where the network performs the worst. And what we can see here is that they are mostly situated here, close to the bricks, and also very close to the sources. And that might indicate that the network has some difficulties performing at such locations. On the other hand, many of the remaining grid positions, for example here in this open space, do not seem to have these high errors. And that's indicating that the network performs very well on these cases already. So if you want to now improve your network performance and maybe get the last bit of quality out of your network, you would have a closer look at these configurations and see how your network or your algorithms could work better in these cases.